Hey everybody, welcome to the channel. I have another video for you today, this time involving friction. This is for dynamics, the module 2 topic for year 11 physics. So let's take a look. So this question comes in as a special request from Daniel. It involves a car that's towing a trailer in one instance, as well as a car without the trailer. So what are we told in this question? We are told that, so just let me set up my pen. We are told that the mass of the car is so I'm going to say MC is 1400 kilograms. We're told that it can produce an acceleration, a max acceleration. So I'm going to say max acceleration of 12.5 meters per second squared. And when a friction force of 5,000 newtons is operating. So I'm going to say the friction force is equal to 5,000 newtons. So in the second case, so this is case number 1. So this is the case when the car is by itself, and this is case number 2. So when it is towing a 500 kilogram trailer, so I'm going to say MT, so the T is for the trailer, so that's 500 kilograms, and it can only produce an acceleration of, so I'm going to say A max in this case is 4 meters per second squared. So now we're being asked to draw a diagram to show all the forces acting on the car as it accelerates at 12.5 meters per second squared. Alrighty, so let's take a look at how we might do this. So I'm just going to use the same diagram here instead of like redrawing this, but I suppose if you were doing this for homework or if you're doing this for an exam, you would have to redraw it in some way. So you can realistically just draw it as a block, but you know, if you are more artistic, you can draw it as a proper car. So anything with mass, we know has a weight force. So, this has a weight force down. So I'm just going to put W as the weight force. And because it's on the ground, the ground isn't shown here, but it's on the ground, it also has an equal normal force. So we make the assumption that the normal force is equal to the weight force if the car doesn't sink into the ground or suddenly fly up. Now, what else do we have? We have the friction force, and the friction force is always against the direction of motion. So we say FF is in this direction, and then we also say that the, so I'm going to draw this arrow longer because we know that the car is accelerating in the positive direction, and we can call this the FE force, or the engine force, okay? So realistically, you can designate these something else, but FF will stand for the friction force, FE will stand for the engine force, which is moving the car forward. So what you might notice is the N and the W arrows are approximately the equal length because I'm trying to say that they're equal but opposite. But in this example, I'm saying that the engine force is larger than the friction force because it overcomes the friction force and it is able to accelerate. So that handles part A. Now let's move on to part B. So I'm just going to have to give myself a little bit more space. In part B, we're asked, what is the maximum force that the engine of the car can produce? All right, so the maximum force of the engine in the first example, you would have to consider, so I'll just make it so you can still see the question. The maximum force of the engine, you're being asked, okay, so part B, we're being asked to find the engine force. So this force here, what is it? Now, if you use Newton's second law, so you use Newton's second law, the sum of all forces is equal to mass times acceleration. Now, when you consider the sum of the forces, you have to sum all of the forces, but because N and W cancel out, you can realistically say, so I'm going to set up some positive axes as a convention. So I'm going to say, this is positive and that's positive. So realistically, you can say N minus W plus F E minus F equals to mass times acceleration. And so because we said N and W are equal but opposite, these two cancel out. Now, when you consider FE is unknown. And FF, we're told it's 5,000, and 5,000 will act in the negative direction, which is why we put the negative here. So we say negative 5,000 here. And then in this scenario, we're just considering the car, so the mass is only 1400. And then we have acceleration. And if you work that out, you will get F E. So the acceleration, in this case, we're actually told the acceleration is 12.5 meters per second. So I just made a mistake here. 12.5 meters per second squared. And so we're told that, yep, so 12.5. And basically what you really get from this is, if you take out your calculator, you get the result 22,000 newtons, 22,500 newtons. And because newtons is a vector, you should always give a direction. So even though this is all relative, you can say in the direction of motion. And that's enough. So that answers part B about the maximum force that's produced by the engine. And now part C, we're being asked, what is the net force acting on the car-trailer combination? Okay, so now we're dealing with scenario number 2. So the car is now dragging the trailer, which is 500 kilograms, and you max out at 4 meters per second squared this time now. So, all right, so part C. So this is actually like a shorter part of the question. Yep, part C. So the net force, so we use F equals ma of the sigma sign. So we're told that the mass, so because this is both the trailer and the car now, we have to add the mass of the car, which is 1400 kilograms, plus 500 kilograms for the trailer. And we're told that the max acceleration now is only 4. So therefore, it's 1400 plus 500 gives us 1900. Then 1900 times 4 gives us 7600 and newtons. And of course, again, in the, sorry, apologies, that's messy, direction of motion. Great. Now, part D. How much friction does the trailer produce? Okay, so how much friction does the trailer produce? So we're already being given the friction that's provided from the ground to the car, but we're not given the friction that's applied to the trailer itself. So in this question, part D, what we're being asked is what is the friction force to the car? Sorry, to the trailer. So I'm going to call that F, and then I'm going to put a T here as well. So the friction for the trailer. So let's grab this image. I believe I have some trouble with that. And then so I'll just snip the image here. And then I'm just going to paste the image again down here, just to give you guys a better example. Oops. Yep. Alrighty. So in this example, let's draw all the different forces that are present. Okay, so we have the weight force of the car, of course. We have the normal force of the car, so N. So now I'm going to use subscripts. So I'm going to say C for the car and T for the trailer. So the trailer, we're going to put WT, and I'm going to put NT for the normal force for the trailer. Then what else do we have? We have the engine force, of course. So the force from the engine, but we also have the friction force of the trailer. So the friction force from the trailer, but we also have the friction force from the car. Okay, so we have 2 friction forces here. Now we're being asked to work out the friction force from the trailer. So this FFT value here. Yeah, so I'm just gonna put this question mark because that's what we're trying to find out. So to be able to work this out, again we use Newton's second law. So F equals ma. So Remember how in the previous example, we were able to ignore the normal and the weight force because they're equal but opposite in magnitude. So that applies for the car as well as the trailer. So for this, I'm just going to ignore them completely for now. Realistically, all you need to consider now is just the engine force and the two friction forces. Okay, so the engine force, let's designate that to be positive. So the positive direction we say is to the right, or in the direction of motion. Now we put a minus. We put a minus FFT and minus FFC, the two friction forces, and that equals to MA. Now we have the engine force. We already worked that out in part B. So in part B, you'll remember that the friction force we worked out was 22,500 newtons. So that minus the friction force from the trailer, which we don't know, and the friction force from the car, we're told from the question that it's 5,000 newtons. And the mass here, because we need to consider this whole thing as a system, we actually have to add the mass of the car to the mass of the trailer. So you get 1,400. So instead of working that out, because we actually already worked out the net force in part C, so we can directly substitute 7,600 for MA. So I'm just gonna clean that up. So this part, this right hand side, this MA bit, it just works out to be 7,600 because of what we worked out in part C. Now this reduces quite simply, so all you really get is negative FFT is equal to 7,600 plus 5,000 minus 22,500. And if you use your trusty calculator, you use your trusty calculator, you end up with a value of FFT being 9,900 newtons. And because this is friction, and we need to give it direction, in direction opposite motion. So we give this kind of relative description for the direction because you can't realistically say it's moving to the right because originally this question did not have a diagram. All right, so that's part D. Now looking back at the question, part E, what is the tension operating in the tow bar of the car? So that's a bit of a confusing request, right? Because it's like, you know, in what part of this do you really consider the tow bar? So let's take a look at this now. So I just need to give myself a bit more space. All right, so part E, and I'm just going to snip the diagram of the trailer to be able to isolate the trailer. All right, so part E, imagine if you're just considering the trailer by itself. So I just move this a little bit. It's not liking that. All right, I'll just leave it here. All right, so imagine you're just considering the trailer by itself. Now, the trailer, you have a normal force, of course. You have a weight force. So I'm just going to put the T's here, I guess, just to make sure it's clear that it's a trailer. And you have the tension force because where the trailer is connected to the car, it's at the trailer. So what is actually driving the trailer is the tension in the tow bar. Okay, so that tension is being provided from the engine force, but we need to consider how much force is in the tow bar itself. So if you imagine the tow bar force, so I'm gonna say I'm just gonna put this as T for tension force, and of course you also have the friction force that we calculated previously. So FFT, friction force to the trailer. So in this example, again, we're gonna have to make use of Newton's second law. So it's a very handy law. F is ma. And what we have is, okay, so because we always said the direction of motion is the positive direction, we're going to say T is positive, FFT is negative, and then we say MA. So again, I ignored the normal force and the weight force just because they're equal but opposite. It's a little bit cut off here. They're equal but opposite, and they cancel each other out. So all we're really left with is these two forces. And in this example, so we don't know the tension force, but we did calculate the friction force in the previous example to be 9,900 newtons. So in this part of the example, the mass is only considering the trailer, and the trailer is 500 kilograms. And we know that we're being told in the question that the trailer and the car move at 4 meters per second squared. So this times 4. And if you, now that you only have t as the unknown, you can work this out to be t is equal to, that's reduces to 2,000 plus 9,900. And that works out to be 11,900 newtons in the direction of motion. Alright, so that concludes this 5-part question that involves friction, as well as a slightly confusing concept where you have a car dragging a trailer. So I hope this wasn't too bad. Let me know if you have any questions about this. I can help follow up. I hope you enjoyed it again. Please stay tuned for the next video. Thanks and bye for now.